We now define a second operation involving the multiplication of two vectors, the cross product. This is a multiplication operation that is defined to yield a vector, the magnitude of which we'll discuss shortly. The direction of the vector resulting from the cross product is defined to be perpendicular to the vectors involved in the product. We can see from the middle figure that vector C resulting from A cross B is defined to be perpendicular to the plane defined by A and B. There are two perpendicular directions to the plane defined by A and B, so what direction do we choose? As shown on the right, the direction is defined by the right-hand rule, where we orient our right hand so that our fingers point along the first vector, which is A. Our palm is oriented so that it faces the second vector, B, and sweeping our fingers into a fist from A towards B results in our right thumb pointing in the direction of C. How is such a multiplication operation useful? When forces are applied to bodies as opposed to particles, it is possible for those forces to impart rotations in addition to translations. When the line of action of the force does not move through the center of the body, we say that the force is eccentric. If vector A is a relative position vector from the body's center to some point on the line of action of the eccentric force, and vector B is the force itself, vector C, formed from A cross B, is a load that tends to impart rotation about the axis coincident with C. We call this load the moment of the force. If the body is unrestrained, the moment of the force imparts rotation about the axis aligned with C. For this reason, the cross product is especially important in a body's rotational dynamics. The vector product A cross B is defined to have a magnitude formed from the product of the magnitude of A, the magnitude of B, and the sine of the angle theta formed by placing A and B tail to tail. As with the dot product, the angle theta is permitted to have a range of 0 to 180 degrees. Given this range of theta, the cross product magnitude is either 0 if A and B are parallel or pointing in opposite directions, or positive. The magnitude is never negative. The direction of the vector product A cross B is defined from the right-hand rule. Given the definition of the vector cross product, the cross product can be shown to obey laws of operation similar to those obeyed by the dot product. The one really important exception to this is the commutative rule. We are accustomed to thinking that order of multiplication makes no difference. A times B is the same as B times A. But this is not the case for the cross product. If we consider the direction mandated by B cross A, we point our fingers along the first vector, B, then orient our palm so that it faces A. If B is in the background and A is in the foreground, this requires us to turn our right hand upside down relative to the orientation needed for A cross B. Sweeping our fingers from the background towards the foreground then results in our thumb pointing in the opposite direction from that formed from A cross B. This gives us a special and unusual commutative relationship for the cross product. B cross A is equal and opposite to A cross B. When we define the moment of a force in Chapter 4, this will require us to form the moment from M equals R cross F. It is not correct to say that the moment is F cross R. Given the distributive and scalar multiplication properties of the cross product, we are able to write the cross product of two three-dimensional Cartesian vectors as a sum of 9 separate binary cross product operations involving unit vectors I, j, and k. The results of all those operations are listed here. The magnitude of the cross product operation applied to a set of mutually orthogonal unit vectors is either 0 or 1. The cross product of any unit vector with itself yields a 0 vector. since the angle between a vector and itself is 0 and the sine of 0 is 0. The magnitude of the cross product formed between a unit vector and any other mutually orthogonal unit vector is 1. The direction of the latter operation is in either the positive or negative direction of the third mutually orthogonal unit vector, depending on the order of the cross product. Half the operations are positive and half the operations are negative. As an example, I crossed into j produces unit vector k, but j crossed into I produces unit vector minus k. When we employ these results for the cross product between two three-dimensional vectors having non-zero components in each direction, the results are as shown here. This result is not nearly as simple as that for the dot product. Now we have a vector expression. There are 6 terms, and half of those 6 terms are positive and half are negative. We could simply commit this expression to memory, but there are alternative ways of forming the cross product that are more visual and that many people find more appealing. We have already discussed the definition of the cross product and the term-by-term expansion that follows from the laws of operation associated with the definition. We are now going to talk about the expansion of something called the determinant. A determinant is a mathematical property of an array of numbers and belongs to the field of linear algebra. No prior experience with determinants is necessary, but there are a couple of quirky things that result from the procedures that follow, and if you find yourself asking, why is that there, the answer is that some feature of linear algebra requires it to be so. For now, this simply represents a visual way of arriving at the result at the bottom of the previous slide without having to commit that result to memory. In our first arrangement, we begin with the determinant, which is the 3x3 array of symbols shown here. The first row consists of the unit vectors I, j, and k. The second row consists of the x, y, and z components of the first vector in the cross product, and the last row consists of the x, y, and z components of the second vector in the cross product. We then reproduce the I and j columns at the end of this 3x3 array to form a 3x5 array. We then form terms from the product of the unit vectors and the scalar components of the two vectors along diagonals of this 3x5 array. If we are moving from upper left to lower right, the red diagonals, the terms are positive. If we are moving from upper right to lower left, the blue diagonals, the terms are negative. Collecting all 6 terms about the appropriate unit vectors reproduces the term-by-term result at the bottom of slide 5. For many people, this is an easier way to construct the cross product than committing the expression at the bottom of slide 5 to memory. Yet another way of evaluating the cross product involves something called a cofactor. Like the determinant, this is a concept from linear algebra, and you need not concern yourself with what it is. The procedure involves summing 3 terms, each formed from a smaller residual array, resulting from striking out the row and column of a particular unit vector. If we want the I component, we strike out the I row and I column, so that we are left with a 2x2 array involving the y and z components of the two vectors. The scalar magnitude of the I component results from the sum of the diagonal products, with the sign positive if upper left to lower right, the red diagonal, and the sign negative if upper right to lower left, the blue diagonal. The j and k components are formed in a similar fashion. One important detail to keep in mind with this method is that the sign preceding the whole j component must be negative. Why is this? It has to do with the nature of a cofactor, which we haven't explained. Many people find this way of constructing the cross product appealing, but the one drawback is that we have to keep in mind that the sign preceding the j term is negative. It is up to you to either commit the term-by-term result to memory or use one of the visual aids involving the determinant. Any one of these approaches gives the same result. As a last operation, we introduce something called the mixed triple product, an operation that involves both a dot product and a cross product. Here we are dotting vector c into the vector formed from the cross product of a and b. We could perform this operation in two steps, first by taking the cross product of a and b, and then in a separate operation taking the dot product between c and the vector resulting from the cross product. Instead, we can evaluate this in one operation by replacing the array of unit vectors in the cross product with the scalar components of c. Using the cofactor expansion of method 2, we have c dot a cross b is equal to cx times aybz minus azby minus cy axbz minus azbx plus cz axby minus aybx. Since all the quantities in this array are scalars, the mixed triple product also produces a scalar. You may wonder what circumstances lead us to use this operation. Again, the moment of a force gives us a load that tends to impart rotation of a body about an axis. But it may be the case that a body is partially constrained and only free to rotate about a specific axis. If the moment of the force is not aligned with the free axis of rotation, then only a fraction of the moment will be available to impart rotation about that axis. This situation may arise in a machine where connected elements are hinged along some axes, permitting relative rotation in specific directions. In this case, we may want to find the projection of the moment along the free axis, which would involve taking a dot product between a unit vector aligned with the free axis of rotation and the moment. So, in one application, c is a unit vector aligned with the free axis of rotation, a is a relative position vector from some point along that axis to some point along the line of action of the applied force, and b is the applied force, and we interpret the result as the amount of the moment of the force available to affect rotation about the free axis. Finally, note that a mixed triple product must involve the sequence where the cross product is evaluated first and then the dot product follows. It makes no sense to talk about c cross quantity a dot b, since a dot b yields a scalar and we can't take the cross product between a vector and a scalar. Only the mixed triple product c dot quantity a cross b exists.